Well, but it is already different from that talk.
We hear even more than you are saying.
Okay, I think probably essentially everyone's here. So our third speaker this morning is F.K. Summersalo from Case Western Reserve University, and he's going to speak on Bayesian preconditioning for truncated Krylov subspace regularization with an application to magnetoencephalography.
Okay, thank you, and thank you for the invitation. And so, lots of words in the title, combining things that are not often combined together. So, basically, I'm going to talk about AX equals B. With, being proud of talking about AX equals B. So that's what this talk is about. And so this is a joint work with Daniela, who just gave her talk, and Laura Homa, who defended her thesis last spring on this very topic, and Alexander Hoover, who was an undergraduate at the time we were doing this research. He's now a graduate student elsewhere in applied math. So this talk is mostly based on this first paper, which came out in Science Journal of Scientific Computing last summer, and there are, however, some ideas which are already in the earlier paper that we published in 2011 in inverse problems. So I start talking about the linear algebra part, because if I start with MEG, what happens is that then you maybe don't see where the linear algebra comes into play, because there are so many things that you need to keep track of. So before talking about the application, I clean the slate and talk about AX equals B. So we all know this famous inverse problem. You measure B, which is a noisy vector in Rm. You have a matrix A, which is badly ill-conditioned, and typically in our case, the number of rows is much less than number of columns. So we are talking about MEG devices, and so one MEG device typically have like 300 channels, and so M is 300 in one time slice. But of course, we are going to stack all the data in a big vector when it keeps coming. So M is large, but it's much smaller than what N is. So we are talking about a large-scale problem, and so therefore, solving this problem is something that people have done a lot, but we want to do it fast, and we want to find a clever way to incorporate also prior information, which makes at the end of the day the problem nonlinear. So that's why we are sort of focusing on this simple-looking problem. So if I give this problem to any one of you or to our students, how to solve this and I say that A is ill-conditioned, probably the standard reply would be, let's try Tikhonov regularization, which is a nice answer. So instead of solving the B equals AX problem, we solve a nearby problem where we minimize the residual B minus AX norm, and then we add a regularization term penalizing the growth of X. And alpha is the regularization parameter, which we typically choose by, let's say, using the discrepancy principle. So that's how it works, of course. Now, there is another alternative, which is in particular popular in problems where the matrices are large or huge, and that's to use the Krylov subspace method. So I'm talking here about CGLS, conjugate gradient for least squares problem, which is one example. There are many others. So let's look at first the Krylov subspace, which is the span of a number of vectors where you take the normal vector, your normal equation, so you multiply through your equation by A transpose, so that your A transpose A is a square matrix, and so you can hope to be able to use the conjugate gradient for the problem. And so then you start forming these spanning vectors. You take your A transpose B, which is essentially the unfiltered back projection if you want to talk about tomography, and then you iterate A transpose A several times, and so you get this space K, Krylov K subspace, which is the span of those vectors. And now you define xk to be the minimizer of the A transpose B minus A transpose A x norm in that Krylov subspace, and the CGLS algorithm, which I'm not stating here, is a fast and efficient way to do this calculation. So there's an effective updating formula which requires for each update, when you're adding one dimension to your Krylov subspace, you are required to calculate only two matrix vector products, and the memory requirement is minimal. So it is a very efficient way to iteratively solve AX equals B in the least squares sense. So that's pretty standard. So I'm not going into details of what you have here, but I simply indicate A and B. So those are the matrix and vector that define your problem. X0 is the initial value where you start your iteration. So you could think that it's A transpose B's in this case where you start your iteration, and K is the number of iterations here. So now I say alternative. So alternative to what? Alternative to Tikhonov regularization. So there are classical papers saying that you can use the Krylov subspace method as a regularization scheme by stopping early the iterations. So you don't go all the way to the convergence, which would be the pseudo-inverse, because that pseudo-inverse is, of course, dominated by noise. So you start iterating, and you follow how your solution is doing while you iterate, and you stop at K where you satisfy the discrepancy condition that your B minus AK is more or less about the size of the noise level. So you stop your iterations there. And this iteration is known to work pretty much like Tikhonov regularization. So qualitatively the solutions look similar. So you don't go and resolve the high oscillations. You solve only low order modes, so to speak, from your data. So it's kind of a smoothing procedure. So when we are doing the MEG problem, we could do this. So you take this AX equals B. I'm going to explain in detail what the problem is, but I'm going to have a big AX equals B problem. So we could do simply CGLS. But we want also to incorporate some prior information about the solution. This solution in MEG is, of course, non-unique. You see it immediately if you have thousands of degrees of freedom, and you're measuring 300 channels. So there's no way you can talk about uniqueness. So you need to, of all the possible solutions, choose something that is resembling what you believe that is there in the brain. Now, let's look at an idea from numerical linear algebra that people are using to speed up the Krylov subspace iteration. So if you have AX equals B, and let's say you know some sort of approximate inverse of A, and this is typical, for instance, in finite element calculations. So you can try to make your problem a little bit better by using those approximate iterations, by introducing what are known as preconditioners. And so you can use left or right preconditioners. And in this formulation here, I have put both of them. So first of all, you can multiply your equation through by a matrix R, which would be the left preconditioner. And then you can also replace your X by M inverse W. So this is X here. So this is the same problem, but then if you solve this for W, then you have to solve for X still from this equation. And so this is typically done in numerical linear algebra to speed up the iterations. Well, in inverse problems, that's not exactly what we want to do. So it's not that we want to go faster to the bad solution. So we want to go we want to guide the solution using the information that we have. And so therefore the design of these preconditioners should be based on our information, what we believe that it's there. And so that's what the term Bayesian preconditioner refers to. So we are, instead of trying to speed up the iterations, we are trying to guide the solution in some smart way. And before I do that, I mentioned that there's something which is called flexible preconditioning, which you can find, for instance, in the book of Yusuf Saad. So in flexible preconditioning, you change the preconditioners at some point. So you start your iterations using preconditioners, and then after some number of steps, you restart your iterations by changing the preconditioner. So in this case, I'm having a family of preconditioners, ML, where L is from 1 forward. And so then what I do here, I simply use the CGLS to solve the precondition problem with my preconditioner ML. And then at some points, I have some discrepancy criterion, for instance, at which I stop this iteration. When I reach that, I change my preconditioner M, and then I restart the iterations. And so now you might wonder why I would like to change the preconditioner, and there will be an explanation later why I do this. I want to show you that there is an algorithm that pretty much resembles what we are going to do. So we are going to change the preconditioner while we are moving. So it is kind of a flexible preconditioning scheme that we are suggesting to use to this MEG problem. So what is the stopping criterion here? Well, the stopping criterion could be that when x is not changing significantly, you stop your iterations. And inside, in the inner iteration, you use this discrepancy condition. Sorry, I take a little bit of. Okay, so this is all what people do in classical linear algebra community. Now, what is the Bayesian preconditioner? So let's look at the inverse problem using the typical Bayesian terminology, and I'm looking only at Gaussian case. So you will see how we get rid of that later. But so suppose you, as is common in Bayesian framework of inverse problems, you define some prior information that you believe is true for your x. And so in this case, I'm assuming that my x is a priori normally distributed random variable with 0 mean and covariance gamma. So this is my prior condition at the moment. And what about the likelihood? Well, I have ax equals b, and so likelihood is answering to the question, what is the probability distribution of b given x? Well, if I have a model b equals ax plus noise, and if I know x and noise is 0 mean, then of course the mean of b would be ax, because the expectation of noise is 0. So I have additive noise here. And what is the variance? Since x is fixed in this scheme, so the only variance comes from the noise, and so therefore the conditional distribution of b given x is just Gaussian with mean ax and covariance c. And so then we go, as we do in the Bayesian framework, we ask what is the posterior distribution of x given b. And so what you know from the general theory, so x is again a Gaussian, so the posterior density is Gaussian with mean x bar and covariance g. I'm not so much interested in the posterior covariance in this talk, so I'm concentrating on the mean, and the mean is found by since we are in a Gaussian framework, the maximum a posteriori estimate and the conditional mean estimate is the same, and so you can formulate your conditional mean as a solution of a minimization problem where you have the likelihood part. So this notation C index here means that we are calculating the inner product with weight C inverse. So this is the likelihood part, and this is the prior part. And so if you minimize this, you will get the conditional mean x bar. And so here's the minimization problem in a pure Gaussian problem. So what does this have to do with preconditioning? I have written here the term prior conditioning. So we call prior conditioning this way of choosing these preconditioners based on prior and also based on likelihood. So here's a connection. If you write your inverse of the covariance matrix, or if you like the precision matrix, the prior precision matrix as M transpose M, where M could be the square root of this matrix or the Cholesky factor of this matrix, is your choice. We need just to have a symmetric decomposition of our matrix gamma inverse, and likewise for C inverse. So notice gamma and C are, by assumption, they are symmetric positive definite functions. So you have the inverse and you also have these symmetric decompositions. So then if you go back and look at this formula here, you plug in C inverse and gamma inverse those decompositions, you get a quadratic form where you have R times B minus AX plus MX. And now it starts to look a little bit like what we have seen before here. So we do whitening at this point. So we say, well, let's say that instead of solving X, we are solving W, which is M by X. And so if MX is, I mean, you see from the form of your prior that this W is going to be white noise. So it has mean, zero, and covariance identity matrix. So this is the whitening transformation, or Mahalanobis transformation in statistics. So we do this transformation. We plug in this W, or rather we solve for X and we plug X in this expression here, and so we see that the minimization problem is RB minus RAM inverse W squared plus W squared, where W is MX. And so if you look at this formula now, you realize that this is actually nothing else but, or you can interpret it as a Tikhonov regularized solution to B equals AX with preconditioners. So we have M, which comes from the prior, we have R, which comes from the likelihood, and we have a penalty term with the Tikhonov parameter equal to 1. But so you can say that what you're looking at here is simply a Tikhonov regularized solution to AX equals B using those prior conditioners. So now you see the story. So we are going to use flexible GMRes, or flexible iterative approximations for solving our ill-posed problem B equals AX. And so we are introducing this R and M from the statistics of the problem, so from noise, from prior. So let's go to the application now, so you see where we want to use this. So here you see the device, the MEG device. So there's a big door where you have the squids inside, which are measuring the extremely weak magnetic fields that the brain activity is creating outside the skull. And this is all in a magnetically shielded room. So the magnetic fields are of the order 10 to minus 15, I think, Tesla. So femtotesla. So they are several orders of magnitude smaller than, for instance, the magnetic field of the Earth. And so you really are measuring something which requires a quantum device, or squid. And so here is the magnetic, here is the MEG device dismounted. So here you see the gradiometers. So what they're actually measuring are the tangential gradients of the normal component of the magnetic field outside the head. So you have these H-shaped loops here. And if you count all the channels, you have a little bit more than 300 of those channels that you are observing. So this is the helmet inside the door. And so here is an example picture of brain. So we want to locate activities on the cortex. Sometimes we also want to see inside the brain, so we may have a three-dimensional problem. Often, however, people are only concentrating on the cortical layer, so pretty close to the surface of the brain. And so this is what we try to do here. So let's write what this A and B are in my linear problem. so that you see a little bit of the dimensions and where the problems lie. So, so we use the quasi-static approximation of Maxwell's equations, and so D is the domain in R3 that is modeling the brain tissue, and sigma, if you want to introduce also the effect of volume currents, is the electric conductivity. And so you have the total current, which is the impressed current, which is the sort of the postsynaptic current, which is stable for about 1 millisecond. So you have several of them. So you have many neurons which are bundled together, and you see these millisecond range small impressed currents there, and then you have the return currents or volume currents, which are just the ohmic currents inside the head. So we are not really interested in the sigma E. That's going to be part of the noise that we are going to look at. So I'm trying to build a model where we take into account all kinds of effects that are there in the head, so that we can concentrate on the impressed current. And so we need to do a little bit of modeling here. So that's the basic model. And so then we use the Biot-Savart law, saying that the magnetic field generated by the total field, assuming that the magnetic permittivity is constant, which is a good approximation in biological tissue. So B is obtained by this integral, and R is the field point which is outside the head, and R prime is the source point inside the head. And so this J total is the source for the magnetic field. Now, we are measuring the magnetic field outside the head and only some component of it. So, but we also discretize this integral. So if you want to discretize this integral, you can use Gauss points, use Gaussian quadrature. You can use Monte Carlo integration, whatever you decide to do. So, but the most common way of doing it is to approximate your J, and so we adhere to this sort of paradigm here. So we say that the total current is a sum of pointwise dipoles. So Q's are dipoles at points Rn. So these are vectors, and Rn's are the locations. And so if you want to express these Q's in a local frame, so J1, J2, and J3 are the local frame vectors, and Sn's are the coefficients. So you get this sort of discretization of your current, and then you plug in this total current into your Biot-Savart law, which then discretizes your integral into a finite sum of the dipole responses. So here we go. So I plug in those dipoles in the Biot-Savart law, and so my integral becomes a sum. And with point evaluations of the kernel, which is here, you have the basis vectors, and then we are measuring in this explanation. I'm taking only the normal vector of the magnetic field. So as I said, the gradiometer measurement is actually taking the tangential gradient of the normal vector. So they have these H-shaped loops, which takes the field in minus field out in a little bit offset positions. And so that's approximation of the gradient in that direction on the surface. But that doesn't change really the main point here. So you have this equation, and so this is obviously some linear problem. So you have some linear matrix here. LMK is the component, and S and Ks are the coefficients of your dipole, these local frame vectors. So these L matrices are called the lead field matrices, and so these SNs are the dipole vectors. And so now what people often do, and we also do in this particular example, so we assume that since you know from physiology that the neurons are organized in bundles almost normal to the cortical surface. So since the impressed currents are supposed to be created by those neuronal bundles, you can, or people do in this field often, they approximate that the direction is normal to the cortical surface. This is not necessary. You can do this discussion is not really limited to that, but our simulation is done that way. So we actually fix in our simulation, we fix the direction of the dipole field. It's, as I said, this is not crucial. So here is here I do the fixing of the dipole field. So my QNs are normal to the cortical surface, and in our model we are using the Montreal Neurological Institute brain model, which you can download if you want to play with those, which has something like 15,000 nodes. So it's pretty dense, based on MRI images. And so we are in this computed example, we are estimating these QNs, which are the dipole strengths in these spaces. And so in this case you have AX equals B model, which is now looking as follows. We have these magnetic field components at time t. So this is going to be time dependent problem. And so we have these matrices LM and so the activation is changing in time. And so these elements here, they can be computed with various accuracy. So you can include the volume conductivity into this LM if you wish. So you can express your volume current in terms of the impressed current, and so you can then make the problem linear if you know the conductivity distribution. So this is not really, again, so much importance. I will explain what we are doing in our model. But so you have a way to calculate these matrix elements LMN, and so then you have this linear problem. Now we are going to use the following notation. So we are registering the magnetic field at different time instances. So these MEG machines are taking measurements every millisecond. So that's the time resolution, and so you are measuring 1 minute and you get a huge amount of data. And so obviously if you want to do something that is useful, you have to speed up the calculations, and that's why we want to do these fast methods to estimate these dipole activity. So we have these B's, and I take at each time slice a vector of size m, and then I'm stacking them into a vector. So now I have my data, which is of size mt, where m is typically 300, and t is as many time slices as you want to include into your data. And so then here is the unknown. So the activity is also changing in time. So n is of order of thousands, and then you take as many time slices as you want. And so each B is related to Q by this matrix L, and so this big B matrix and this B vector and this big Q vector, they are related to each other by this L script L operator, which is block diagonal, which is just a Kronecker product of the T identity matrix and this L. So we are repeating our lead field matrix and in the diagonal. So this is sparse matrix, although the blocks are not sparse. The diagonal blocks are not sparse. And so now we have this nice B equals LQ, so B equals AX type problem here. And so then we have to decide how to solve this. And so here it is important to introduce some sort of prior information about what you believe that the activity looks like. So I'm assuming additive noise, but this additive noise is just the noise is not only the device noise. There are lots of other things going on in the brain. So if you, depending on now what you want to do, so MEG is used as in medical applications, for instance, to localize the onset of epilepsy. So that's a spiky activation somewhere in brain. But of course, the brain is not standing still when you're measuring this spike. So there's lots of spontaneous activity going on all the time. So the noise is rather complicated, and the noise is a real problem because it comes from the same source. So it's not outside noise which is independent somehow, or really different from what you're trying to recover. So the noise is really coming from the same source, and so this is the real problem. And so what we are interested in some particular specific signal, and so the rest of the brain activity has to be somehow lumped into the noise term. So E is the device noise, and D is what brain is doing all the time. And this D actually has an amplitude which is of the order of magnitude of the activity that we are interested in. So this is not low noise at all. So this is in many ways a bad sort of situation. So here's what we do for modeling the noise. We based our noise modeling on a paper by De Monk and others from late 90s, where they had developed this nice model called POMAM, which is as follows. So suppose you want to estimate, let's say, model the alpha wave of the alpha activity of the brain. So what they did, so alpha activity is about 10 hertz. So what they did, they put random dipoles into the brain, and then they turned them randomly on and off, and these random dipoles are oscillating with a frequency around 10 hertz. And so these intervals are drawn from Poisson distribution, and also when they are on and off, and which dipoles are on and off are drawn from uniform distribution. So you have this random dipole model with random excitation. You have this typical 1 over f, 1 over frequency noise in brain, so that's included in the noise model. And then we have also added the measurement noise in our noise model. So here is a covariance matrix that is based on calculations based on simulations using this POMAM model. So this is the covariance matrix, autocovariance function of the signal. So it looks like this. So you have typically here, this is 10 hertz. So what we do, we use a covariance which is a Kronecker product of spatial and temporal, the temporal and spatial part. So we have the temporal part, which is based on this alpha noise simulation. It's a Toeplitz operator because we assume stationary noise, and then we have a spatial part. And I'm not going too much into details. I just want to give you an idea that we are not using, a stupid, white noise model for the brain activity. This wouldn't work. And if you don't want to use this model, what you can do, you can try to make a measurement of the brain when it's idling, when you know that there's nothing interesting going on, and then you calculate an estimate for the covariance of the brain activity. So this is what you could do in practice. This is for simulation purposes. So we want to see that the idea works with something which is realistic. And so for the measurement noise, we take the famous stupid white noise model. So this is the covariance structure. So it is temporal and spatial. And so then what we use as a prior, well, what we are interested in is in this application that we are looking at was focal sources. So this is when you're talking about epilepsy onset. So you know that there's often spiking which was well localized in space and time. And so, well, we would like to use a Gaussian model, because Gaussian model leads to this prior conditioning concept. But Gaussian models don't favor local and focal sources. So what we do, we use conditionally Gaussian model. So we say, let's say there is a parameter gamma that we determine later. And suppose you know this gamma, then your source at time t is Gaussian. And the covariance matrix is depending on this gamma. And this gamma, on the other hand, we choose to be distributed according to gamma distribution. Why gamma distribution? Well, gamma distribution is a typical fat tail distribution which favors outliers. So we want that there's only few places the variance is high. So we want the variance to be low all over in brain. But at some points, you might have some activity happening. And so, but you don't know where that happens. So let's say that the covariance is following the gamma distribution. Now, gamma distribution, if you draw from gamma distribution, you typically get low values. All of a sudden, there's a high peak. Yes.
In that case, essentially, you assume that there are very few localized spikes. Right?
Laplace distribution. Did you say Laplace?
Laplace distribution. Yeah.
Yeah. That's probably fine. This gamma distribution is nice because it leads to a closed form solution to a problem that we want to solve. So you will see it's related to the conjugacy nature of the gamma distribution. But we are not using that as an argument basically. So we know the gamma distribution favors sparse solutions. So that's basically the sort of the let's say the Bayesian reason. Well, Laplace distribution would be fine from the information point of view.
Yeah.
That's right. Absolutely. So here is the gamma distribution, and so now I make a gamma vector where I have all these variances stacked in a vector of length n theta. This should be up. And so here is the what you get from Bayes' formula. So here is the likelihood part. This is the prior part, and then you have the gamma distribution part. So we have two unknowns. We have q and we have gamma as unknowns. And so my gamma lambda matrix here is a diagonal matrix where I have all these gamma vectors on the diagonal. So the locations of activities may change in time. So I'm not assuming that the spike remains in the same place. So now we do a simple iterative algorithm to find a map estimate for q gamma. So what we do, we initialize gamma to be the constant at the beginning, and then we are updating our q assuming that gamma would be known. And you see this is a purely Gaussian distribution that we are looking at. So this is ax equals b problem here, this one. And then once we have a candidate for q, then we are saying, well, let's update gamma. So in some sense what we are doing, if you think if you just look what we are doing when we are doing the updating of the prior, it looks like we are doing something which is really against the Bayesian philosophy that while the data keeps coming, while the information keeps coming, we update the prior. Well, that's not quite the case because we are really building this prior as a hierarchical prior, and so this allows us to do this in the nice Bayesian framework, so that when you learn about the activity, we try to then learn about the covariance of this activity, and then we go back and update our Q. And so here is the step B when you update your Q. So we assume momentarily that gamma is known, and as you can see, this is exactly the kind of problem that I addressed at the beginning. And so if your gamma is gamma k, you can solve this using CGLS. Few steps. Once you have done it, you go and fix your Q and you update your gamma. Let's go back and see why this works fine. Gamma, the gamma components are all independent. So this is a diagonal matrix, remember. And so if you want to maximize this, keeping Q fixed, you just calculate the derivative of this quantity and write it equal to 0. And there's a closed formula that you can use to calculate the maximizer. And so that's really fast. So you don't have to do any iterations here to update your gamma. And so what this amounts to is that we do this preconditioning step here in the linear problem, and it turns out that the CGLS terminates in 10, 12 steps. So you can see this is really fast. And updating gamma is just plugging into a formula, and all together in this example that I'm going to show, it required only 28 outer iterations. So we are talking about seconds here when we are doing this. And so here is the simulation I have. So this is the brain. So all the calculations have been done using the brainstorm algorithm, brainstorm package, which is an open source package for MEG EEG that has been put together by a group of people working in MEG. So here is the MEG. So here is the brainstorm brain. We have two sources here, and we have a time course for this first source like this, and then time course for source 2, so it's a little bit earlier. And so then we are testing how this works. So here are simulations with the noise. So you see that. So here is the activity, but the background is pretty high. So why is this not around 0? Well, remember we are talking about 10 Hertz activity, and this is this is from 20 to 50 milliseconds. So this is just a snapshot of a slow activity here. So we are interested in time scale which is in order of tens of milliseconds, and so therefore we are windowing our data to be like, I guess we had 15 or 20, maybe 15, yeah, 15 in this example. But so the method is capable of dealing with longer time windows, which we are right now studying in another application. So but you see that this noise is not what you usually encounter. So this is really messy, and it's pretty realistic. So the computed results are we are comparing three solutions. So we are using CGLS without any preconditioning, which is already a good idea. So without any particular preconditioning and with an appropriate stopping criterion, we are testing with left and right preconditioning. And so here are some results. So this is a time slice when none of the sources were active. And so here we have left preconditioner only, which takes care already of the covariance of the noise. This is with left and right preconditioner, so you should see an empty picture, and that's pretty much what you see. So you don't see any activity here. You see traces of activity, which is coming from the fact that we are stopping the CGLS without giving any information for CGLS what side of covariance the noise might have. And so and basically we did this stopping, since if you don't know anything about the noise, what are you going to use as a stopping criterion? Well, I guess we used L-curve criterion here. So there are these activities that could be interpreted as focal activity. So here is a time slice when you have both sources active. So the sources are here and here, and so the left and right preconditioner, they pretty much find them. We were first, when we were running this CGLS algorithm, we thought that we were thinking that the CGLS actually is doing a pretty good job because we see this focal source. But then it turned out that the activity is not at all there. So it's here and here. And so that's really disturbing. If you show this to a doctor, say, well, cut there, that's pretty bad. So these right and left preconditioners are doing a good job. So here we use only the left preconditioner, and you can see that there is some sort of activity at this area, which is higher than what we have here. There's also some activities around here which are then suppressed a little bit when you use left and right preconditioning. And so here is a zooming into these activities. So this is the position where we had the true activity, and so we localize it pretty well using this algorithm. So here is like a cartoon how this algorithm propagates. So you see empty, empty, empty. First activity is turned on, and so then the second is turned on. Here the second is turned off, and so it vanishes, and then you have this empty brain. So you see this, but of course the brain is going on all the time. But that's the point. We don't want to see what's going on in the background, and so this seems to do the job. And I stop my talk with this picture. Thank you. Yes, sir.
Yeah, it's a sort of physical point. So the current has two contributions, as I understand it. There's part from the source, and there's another part which comes from the volume.
Yeah.
Conductivity. How large are the two are those two terms with respect to one another?
Well, the volume source is clearly smaller, but it's not negligible. So there is a series of papers, I think, by Carsten Wolters, who has been doing finite element simulations, detailed finite element simulations. He has shown that if you have strong anisotropies, the volume current may be disturbing, but it's not significant usually. So I think it's of the orders of, let's say, 10%, but I'm not sure about the exact numbers and values. But I think in anisotropic cases, and brain is unfortunately is strongly anisotropic. So when you have anisotropies, you can have some sort of almost like focusing effects. And so that
Anisotropy here is in the conductivity.
Sorry?
It's anisotropy of the conductivity.
Yeah, that's right. Yeah.
Which is due to the fact that the white matter tracks are.
Yeah, that's right. Yeah.
Thank you.
Because some currents are invisible in this MEG
Yeah.
measurements. So how this kernel of the measurement operator affects in this?
So let me see. So yeah. So you have if you have this sparsity prior, it's cheaper for the sparsity prior to say that the invisible currents are not there. So you don't have any clue of the dark currents in data. And if your prior is not favoring them, you don't see them in this. So you just don't see them. Yes. Yeah.
So in the linear algebra community, at least, we worked once on Tikhonov and then CGLS and then the hybrid method, right? When you're over-iterating in the CGLS, in a sense, you're doing usually large by diagonalization, and then you're using the bigger subspace and the Tikhonov on the bigger subspace. And then people claimed, at least, that this is more stable and give you better results. You try?
Yeah. So you mean that we add the Tikhonov regularization and iterate to death?
No. The idea that you take, basically, you replace the CGLS with a large by diagonalization. You iterate more than you need. So, and now you have a small subspace. You have k vectors that you have, and then you're using whatever stopping criteria you want to that particular subspace. So the agreement, at least, was in the linear algebra community that it works better than CGLS, because CGLS, of course, have discrete events, right? So you can sometimes you'll be above the misfit, and then you go beyond the misfit. So it's difficult to exactly adjust it.
I see. Okay. Yeah. So no, we haven't tested that. No, that's true. So what we are testing right now with a different example is what happens if you just don't put the prior in the preconditioners, but you are using it as is, and you're just stacking the matrices together. Yeah.
I actually had worked at that.
Yeah, but not.
Hybrid.
Yeah.
It's
I'm actually not sure that it's
Not
going to
sure
buy
either?
all that much.
Yeah.
I
So
think
we
I think what is making the difference here is the fact that you have this hypermodel which is going to drive you there and is going to tell you where it's going to jump, and the rest is kind of the other one is brutal, so you can play with the parameter. I've done it. It's fun, but seems to be that one is the left preconditioner that's going to whiten the noise, is going to clear the background, and it takes out the problems of the confusing the true signal with the clutter that we're not interested in. But the one on the right is going to be much stronger, and that depends on the parameter, and that's stronger than messing around with this bidiagonalization.
Yeah. So as you see, I'm not the linear algebra person in the room. So in our iteration, the stopping criterion is let me see if I wrote it down here. It's a crude one. So where do we stop? Well, since we are whitening our problem, so we assume that the noise is white. So what is the noise level of the white noise? We take the expectation of white noise squared. So this is the variance, and then we take square root, and so that's an approximation for the standard deviation, and we use that as a measure for the noise level, and that gives the stopping criterion here. So it's a little bit, we maybe had some fudge factor 1.2 or something in front of it, but so this is really a crude stopping criterion. But as you can see, well, it stops really early. So this is really fast. So.
But I mean, I know where Eldad is coming from, because I was coming from the same place. So I was in that corner for a long time. This is you can think of this as being an inner outer. So we're stopping the CGLS on this, which is like the good enough part. And you can think that the outside is like a nonlinear wrapper, and that is stopped when you have a relative, say, change of the order of 10 to the minus 8. So that's pretty tight on the outside, and that's where you get this, 10, 28. And then inside you're solving this, let's say, associated least squares problem. So in a way, the outside is going to fix you what you don't get from the inside. You can think that you don't need to work so accurately on the parameter because you're going to have a lot of parameters. Here you have a parameter per entry, so it's much stronger than working on one parameter in a Tico node. That's the way I interpret this.
There was a question.
Just a curiosity, I think I missed how long it takes for a single time slice computationally,
Very
Um,
an order of magnitude.
let's see, the whole iteration, 20 times 28. For one time slice, I don't sure if he had that timing.
It was very fast. It's extremely fast.
It's
it was
yeah.
12 seconds.
Less than
Seconds
I
for a
think-
millisecond.
no less than seconds.
No. That for the whole.
Yeah, so the
I can give you the
So
numbers
it's
because
in real time.
because
Yeah.
we can I have it. We have recorded it in the thesis.
it's not really real time because the data comes every millisecond.
No,
So
millisecond.
but we can. I think this 20 time iteration. It was like 8 seconds.
And it's broken down. It's actually, if you're interested in the numbers, we have them.
Yeah.
And it's broken down by how long it takes to do each part. And this was done in MATLAB, and it was not optimized. It was just
Yeah, it was not
on a
optimized
regular
at all.
graduate student equipment. So
Yeah.
Well, the reason I was asking is that I was curious to see if this one was taking longer. I was curious to see if you ever consider neural networks for that, just for the very, very fast real-time side of the instrument. I have past experience in using neural networks for neutral emissivity tomography on tokamaks, so nuclear fusion machines.
Yeah.
And basically, I was able to train the model. So I have a model and all these fancy maths and so on. And then you manage to fill the phase space quite nicely. And then the training went quite slow. But then the network was able to cope with very, very high level of noise in the data very reliably. The regularization was fantastic. And I got really great results with microsecond type of application type for the network. So
Yeah. No, we haven't done that. So yes, that's interesting. Yes.
I think maybe there's quite often a sense in which you want something really quick in an experimental setting to see whether there's something wrong. You know, that like you're not going to repeat this experiment, maybe something's fallen off or something. So there's a lot of situations where a quick and dirty algorithm is really important for the experimentalist, but also to have some kind of optimal, slower algorithm when you want to analyze the data. So
Yeah.
maybe that's the kind of thing you're saying.
Yeah. No, I understand. I understand the point. Yes. Yeah.
There's the gamma parameter is related to the variance at each pixel.
Yes. Yeah. That's right. For each pixel.
But you're learning it during the
That's right. Yeah.
in the process. So at the end, what does it look like? Does it look like a large variance where there's a spike? Or no?
It does. Yeah. So you have in a couple of pixels you have. So it doesn't look very different from what I showed as the
image.
As the image. Yeah. So you can also look at the sort of an activity map by looking where it proposes large variance.
And if you wanted to look at the covariance of the posterior, what would you do? You just add that to the diagonal of the Hessian? So the variance of the posterior, let's say, not the covariance. Does that work out the same? You would just.
Oh, you mean if you want to solve the problem?
Well, no. So let's
fixing
say
the variance.
at the point where you've got your map estimate,
Yeah.
and you want to look at the variance of the posterior, you need to add in the diagonal of the Hessian to the prior.
Yeah. So what's right? So that's right. So you use those gammas in the diagonal.
Okay.
That's right.
And does that also follow the form of the image? I mean, does it, in other words, does the
Is the variance
variance
large?
coming from the data dominate over the prior or not? Because that's usually the rationale for choosing. If you
Yeah.
take the sort of classical Bayesian method,
Yeah.
you do it a priori and fix it,
Oh.
and then you would look to see whether the information coming from the data is overriding the prior or vice versa.
Yeah, so we didn't calculate the covariance matrix, posterior covariance in this example. We have been testing it in simpler problems. And so I'm trying to summarize what we have seen. So there is, where you have the activity, you also have larger variance at those points.
Sure. But it's not you're not
It's not the
calculating the
outliers.
variance of, I mean, it's the confidence of your
Yeah,
estimate
well,
of the
you
solution.
see, this is not really a Gaussian problem. It looks like a Gaussian problem.
Locally, it's Gaussian around the map estimate.
So if you assume that it's Gaussian around the map estimate, well, yeah.
I think it looks like if you're taking the gamma and you're plotting it, and I'm not saying this one because this is a stupid example for answering this. It's almost like you're seeing a high pass filter, so it gives you some edges.
Right.
Because as you're moving along, it's like you're putting on your glasses and you start seeing better. So from as you move along, you get the sense of where your solution is going to be jumping, and when you know at the previous step, it seems like you should allow a jump there. Then your gamma becomes
Sure,
larger.
that's in the prior, but the purpose of the posterior is to estimate the confidence of your map estimate. So you would ideally like to have low variance.
Yeah. Now we have done Markov and Monte Carlo with this hierarchical model, but that's pretty hard problem.
Yeah, sure.
It's because not only because of the dimensionality, but there's something which in statistics called blocking. So the Q and gamma, they are strongly correlated. So think about a distribution where you have two variables which are correlated. So you have a narrow channel where you should be able to walk up and down. If you use, for instance, Gibbs sampler, you're doing really slow progress, and you get an over-optimistic picture easily because your sampler is not moving well. And so from the sampling point of view, this is still a hard problem to solve.
Actually, what occurred to me, sorry, what we often do in emission tomography, you just resolve a problem with different instantiations of noise, so you get a sample estimate of the
Like a bootstrap.
No, you just repeat, and so you just have multiple instantiations of the noise and multiple estimates of the map.
Yeah,
So they build a.
Isn't that bootstrap? In statistics, I think so.
Okay, I didn't think it was called that.
Parametric bootstrap is exactly. Yeah.
But then you can just compare the estimates.
Yeah. Well, you can do that, but we haven't done that. So, yeah.
Okay, I think we'll wrap it up at that.
Thanks.